All right. So it looks like there is still some people joining, but it looks like maybe the majority of you are already here. So we can get started, and then if anything, we can, if there are questions at the end, if somebody missed the beginning or something, you can send me a message, and I'll repeat this at the end. So for the people who joined later. So the lecture of today is based on the main properties of nuclear detectors, so detectors used in nuclear and particle physics and in this field. And the main things that we're going to cover today are energy resolution, time resolution, and linearity. And we're going to see why these main properties, and there are a few more, I didn't just want the title to be too large, but we're going to see why there are certain properties of the detectors that are quite general. Regardless of where you work at and regardless of what detectors you have, there are some certain specific things that kind of are in common to all detectors, or rather detector systems. Okay. So the goal for today is I would like you to just think, throughout what is the best way to design an ideal detector system. So, in our field, there are so many different things that one can try to do. There are many different experiments, many different observables, many different particles that one can look at: gamma rays, neutrons, neutrinos. You can try to do an imager if you're trying to find the source, or you can try to do like a spectrometer if you're trying to find the energy. And there is really nothing, no such thing as a ideal detector in real life. There is no such thing as like something that does everything perfectly. But there are some things which, based on the application that you want to use, you can design a detector that does certain things very, very well. And yeah, so let's talk about what are the main things that we can do in our field. Well, so whenever we think about any detector or any sensor that we have to talk about, like, there are a limited amount, a finite amount of properties of these particles. And maybe when you think about a detector, you can think about like a thermometer, or you can think about something like something to measure the pressure of a gas or something else. All these properties that I mentioned now, or the color of something, all these properties that I mentioned now, these are kind of thermodynamic properties. They're properties that arise when you have many, many things together. They're not properties of particles. In our field, in nuclear engineering, nuclear physics, and particle physics, we're really interested in the single particle. And so it doesn't make sense to ask what is the temperature, what is the color. The questions that don't make sense to ask are actually very limited. There is only a few things that fully define a particle. Well, first of all, we have to know what the particle is. So in order to fully define a system of particles, we have to know, whether the particle is an electron, a proton, neutron, neutrino, what the particle actually is. Or maybe it can be even a composite particle, like a nucleus. And the second thing is we have to know at what moment and position was the particle emitted, or we have to know at some point in time and space when where a particle was. At the same time that we know the position and the time of this particle, we also know the direction that this particle is moving. If we know these properties, this can be the direction and the velocity can be both put together as being the momentum of the particle. For those of you who have studied some introductory physics, the momentum in classical physics is basically the mass times the velocity vector. So we can summarize all of these things by thinking about like this thought experiment that Laplace, was a mathematician, thought about in order to figure out everything that happens in the universe. So the Laplace's demon is basically this thought experiment of somebody that has full information about the universe. And all they need to know in order to know everything about the universe is the position of every particle. You can imagine this being, and now it's a good time to start drawing. You can imagine this as being the origin of all of these arrows. So you take a snapshot, a picture of the universe at some point, and you figure out, at some t is equal to t0, you figure out the position of every particle in the universe. And this would not be enough to figure out like all the states at a different time. What you need to know on top of that is also what are the momenta vector. So these arrows here, where is the particle going to move in the next instant? And this would be, your momenta vector right there. Okay, so you can see that there are if I know these properties here, I can fully figure out the entire system. Now, if I also know what are the interactions between the particles, I can basically reconstruct any event in the future and any event in the past, given a single picture of the universe at a certain point. Because we do deal with particles in our field, that is sometimes our goal. Our goal is to try to figure out the position, the time, the direction, and the energy or the velocity of every particle coming out of a reaction. And this is kind of like the holy grail of a detector, something that can figure out every particle produced and the position and the directions. This is why sometimes when you look at the state-of-the-art systems at facilities where they spend billions of dollars for detectors, you see detectors that are huge, many, many times the size of a person. And these detectors, their goal is to try to figure out exactly these properties. There is also, let's see if, next slide. There is also another property of the particle themselves, which is the multiplicity. Now, this is kind of a meta property. It's not a property of the particle, but it's rather a property of the particles. So, in a reaction, you might have a single particle produced, and for that particle, all you need to do is to know the position, the timing, the direction, the energy, and what type of particle it is. But in certain situations, you can create multiple particles in the same reaction. And for each of those particles, you're going to have to specify all of those properties. Now, this is actually something that is very important, because if we, we might specify exactly, maybe we have two particles in the system right there. And we might be able to fully figure out and have a detector over here and fully figure out everything about that particle. We fully characterize the particle, but maybe we don't have a detector on this side here of the room, and we would completely miss that particle. So in that case, we have something that we are actually losing a lot of information because we're not detecting every particle. So we can think about the multiplicity, or just the capability of measuring every particle in a certain reaction. And this actually takes us to the next slide, so to the main, to the first type of characteristic that we can characterize a system by. So the first thing that we can talk about is the efficiency of the system. Now, the multiplicity, when we want to simply measure the number of particles produced, like often throughout this presentation, we're going to simply focus on a single thing. So we're going to not forget everything about the timing, position, momentum, and mass and identity. All we care about, we want to find out what is the best way to measure, to create a detector that is that always detects every particle in the system. That if there are two particles in a system, you can measure both of them, and you can always reconstruct, or you can always determine the number of particles in the system. Well, this is what we would call a multiplicity counter, or it's simply the property of a detector to be able to measure multiplicity. So how would we actually do something like that? How would we create a detector that can create a lot of multiplicities, that they can detect a high number of multiplicities? Well, this is actually given very nicely by some equations here, but we're going to talk about that in a bit more detail in the next slide as well. What we want to do in order to measure every particle in the detector is to maximize the efficiency of the detector system. For example, as I said earlier, you might have particles that are emitted in a certain, two arrows, maybe emitted in the same point, but moving in different directions. And your detector system perhaps just covers one side of the room and does not cover the other side of the room. If you do that, you're almost guaranteed that you're going to lose a lot of particles when they're traveling in the wrong direction. So this is why, in order to accurately measure the multiplicity of an event, you try to cover as much as possible of the sphere around your source of particles. So that means trying to completely cover all the directions around your source. And this is why in certain detectors, either you find a lot in national labs or in other countries where a lot of money is spent, you can see these detectors that are fully covering the source. accelerators, you try to make these detectors as long as possible, such that whichever particle they move in, they're going to find a detector in the direction that they are. Of course, in certain situations, it's impossible to completely cover the sphere, but you really try to cover as many directions as possible around where you predict the source to be. The other property, the other thing that we have to try to maximize is, of course, the intrinsic efficiency. So this means that even though this particle here that we said was moving in the direction of a detector, even though this particle is moving in the direction of the detector, it's not guaranteed that it's actually going to interact. I mean, we know that these newtons and gamma rays, they don't always leave energy. They can go through a material unscattered. This is especially clear when we think about something like neutrinos, particles that can go through, I think, light years of lead without ever interacting. And so for some particles, instead, it's it doesn't have to be an enormous distance, but it is possible for a particle to just go through the material unaffected. So how do we make sure that the particle actually not only goes in the direction of the detector, but interacts with the detector and is thus captured or measured? We have to make sure that the detectors themselves offer a lot of opportunities for the particle to interact. And there are a few ways to do that. We basically the particles are going to interact with atoms most of the times, either the atomic nuclear or the atomic electrons. And the best way to do it is to put as many atoms as you can in the path of the particle. One way to do it would be to make this detector very, 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 very long. Like, as I said, you can make them meters long, kilometers long. Then it becomes very expensive. But ideally, you would try to make them as long as possible, like offer the largest possible path for the particle to have to go through before it escapes on the other side. The other way you can do it is by increasing the density of the material. So, instead of taking this whole long path of a certain material, you can try to compress it in this direction and have something that is much denser and with a similar distance. This is not often possible because certain materials, they cannot always made as dense as one would want, but it's a possibility in some cases. And the third possibility is to try to make the detector of a material that offers a lot of possibility of interactions. Maybe something that offers a resonance, perhaps something that really likes, putting some materials or some atoms in there that really like to interact with the particle that you would like to measure. Or, for example, from your lectures on the gamma ray interactions, gamma rays interact with electrons. So you would want to pack as many electrons as possible in this material. This means choosing materials with a very high density of electrons, or commonly called just the atomic number, Z. So these are just some possibilities of how does the efficiency depend on the shape of your detector. And at this point, I think this is a good way to build the intuition, is just to think, you look at the detector on the internet, or when you can go in person, you just look at the detector system, regardless of what it is. And you should be able to say whether it's a high efficiency detector, something that was made to measure high multiplicities, or whether it's something that was made for detecting, that was not optimized for this kind of analysis. So, for example, a detector that might not be optimized for this kind of analysis is something where the source is on one side of the room and there is a single detector on the other side of the room. If you walk into an experiment like this, you know that this detector here was not optimized for multiplicity distribution, for efficiency. Instead, if you were trying to create a detector that was optimized for multiplicity resolution, for the efficiency, you would want to do, as we said earlier, you would want to do a detector that fully encloses the source and has a significant thickness, whether this is an actual thickness or an effective thickness made up from densities and cross sections. But having large detectors always helps for increasing the multiplicity resolution, for increasing the chances that the particle is going to interact. So up to this point here, we can just say, well, the best detectors in the world And for this thing here, for this multiplicity resolution, the best detectors in the world are going to be something that is completely encases the source, and it's a mile long in all direction. And yes, so if this was the case, then every detector in the world would look like that. If this was the only thing that we cared about was the multiplicity resolution, then every detector would look like that, you know, depending on funding. But everybody would try to get something like that. However, that's not the case. Multiplicity is just one of the many properties of the particle that one can measure. And we're going to look immediately at the one that really competes with multiplicity resolution. So we're going to take it to the other extreme. In this case here, we're going to talk about position resolution. Now, position resolution and angular resolution, those are the next two slides, are kind of similar to one another. You know, if you have studied some introductory math, you know that one can take a Cartesian coordinates, get x, y, z, or one can get spherical coordinates, theta, phi, and radius. And so there is a very strong connection between the position in XYZ coordinates and the position in angular coordinates. Now, if I want to know the position of a particle, I want to get some measurements of where the particle interacted, of course. Now, a detector, it's, you know, for most detectors, this is where the conceptualization of the detector comes into play, because we're going to just assume that the detector does not tell you where within the detector the interaction is taking place. Now, there are some detectors that are pixelated. There are some detectors that can reconstruct the position inside the particle, but a lot of the detectors for neutral particles and for scintillators, and they just simply tell you that an interaction took place within the detector. So let's, for example, make an example, make an instance of a particle starting from a source and interacting with a certain detector. So all you get out of this detector here is a signal saying, you know, a signal, just a pulse that says, hey, there was an interaction happening in this detector. Now, you don't know where in the detector the particle, where within the detector volume the particle actually took place, that interaction took place. So one could assume, for example, the best place would be to assume somewhere in the middle, right there. Now, of course, there are better guesses that one can do, you know, if you know more about the detector and the particle interactions. But we can always start by saying that the particle interacts at the center of the detector. Now, however, in reality, if we actually were able to measure exactly where the particle is, if we had some supernatural power to reconstruct and always know where the particle is, the interactions are taking place, we could know whether the particle is interacting on this corner here, on that corner there, on that corner there, on that corner there. So you can see that there is going to be a spread of where the particle actually is interacting with respect to where we are assigning the particle interaction to take place. And this is actually exactly the role of uncertainties. So in this case here, if I wanted to express my my measurement as a data point, I would put it somewhere in the center and put error bars indicating that, yes, I think it's, you know, like on average, it would have interacted in the center, but it could have been anywhere in those in that range that I put there. So that's one of the ways that we can get error bars from an experiment. Now let's do the same situation with a detector that is much larger in size. Remember that this was what we said was the best way to create a detector for multiplicity resolution, was to make the detector as long as possible in order to ensure that the particle is going to have an interaction. Well, in this case here, we see that the same assumption that the particle interacts at the center is going to lead us to huge error bars right there. So that now when I want to report this measurement and I say, where did the particle interaction take place? My data point there would be huge. I basically have lost a lot of information. I'm very uncertain on where the particle interaction actually took place. Such that in this situation, it's very advantageous, as I say here, that it's to reduce as much as possible the size of the detector, or maybe said in a more specific way, in a more accurate way, would be to reduce as much as possible the size of where you can get position information from. So if you can buy things that can give you a signal within a detector and can tell you exactly where it's taking place, that's very good, but it can be very expensive. And or in general, if you do not have the instruments that can tell you where within a detector interaction is taking place, simply reducing the size of the detector as much as possible is going to give you a much better position resolution than a large detector. Moving on to, as I said, the similar topic, is the other face, the other side of the position resolution is the angular resolution. So the angular resolution is basically the same thing as the position resolution. The only thing is that instead of caring about the x, y, and z coordinates, we look at the r, theta, and phi. Well, in reality, when one talks about the angular resolution, most of the times we actually don't even care about the radius, how deep into the detector the particle is taking place. We usually care about these other two parameters, some parameterization of a sphere around it, some angular, some steradian distribution. In most situations, if we can improve our position resolution of our detectors, so for example, when making very small detectors, the angular resolution also increases. If we know the position of where the particle takes place and we know where the particle comes from, maybe because we know where the source is, then we also can reconstruct the angles very well. The converse of that is, of course, also true. If we don't know where the particle is interacting, we don't know what was the direction that it was moving in. So, okay. How do we actually quantify that? Well, in the for the efficiency, we said that the way we quantify it is how much do we cover the sphere around, and that's just like a proportion of the directions in space that we can cover, from 0% to 100% of the directions. And what is the probability that once you are in the direction of the detector, you interact with it? And that's also a number between 0 and 100%. So and we call that the product of those two, the efficiency. For the resolution of a detector, for the position resolution of the detector, what we do is we define the average error of where the particle is interacting with respect to where we are assigning the interaction to take place. So in that respect, we actually, as I said in the previous slide, the resolution would be measured by the length of these error bars here. Now, these arrow bars here, one can take them to be the size of the detector. In reality, they're just proportional to the size of the detector, even when there is not going to be the same chance of hitting everywhere in the detector, but they're going to be proportional to the size of the detector. One can go into more advanced things, like if you make a detector that is a mile long, and the particles only have a mean free path of a few meters, then it's not going to be the center of the detector. You know that they're probably going to be closer to the face of the detector than in the center. But in general, you can assume that the larger the detector, the more these error bars are going to grow, and therefore the more the resolution is going to be degraded. Let's go here. So I'm gonna finish this slide here. Just gonna talk about position resolution, and then I would like to take some time if there are any questions. And I did that for my first presentation. I thought it worked pretty well. So how would we create a perfect detector for position resolution? Well, one way that we can start doing that is by going to the one that we said would fail miserably at finding the highest multiplicity distribution. So we put a source on one side of the room and a detector on the very far side of the room. And if the detector is very small, then we would know exactly, like if the detector is very small, we would have a very good measurement of where the particle is taking place within the detector. This would also optimize the angular distribution, because then we know that the particle could have only gone within a very small directional spread. And you can imagine that there's going to be an extra dimension that gives us the azimuthal angle. And so we know that this type of configuration with a single detector very, very far away is going to be is going to give us a good position and at the same time a good angular measurement. How would we now we're going to try to combine that and still not completely throw the multiplicity or the efficiency out the window? How would we do that? Well, in the efficiency one, we tried to make a single detector that was very thick and very all-encompassing. What if we, instead of that, we're making a series of detector? Very small detector. Well, I'm not really good at drawing, but you can, like, you know, sectors of a sphere. So all the very long detectors that give you that are, so you still optimize efficiency, they fully cover the source, but are now divided into many different detectors. Instead of being a single cell, it's many different detectors. So such that when you have a particle interacting, you're gonna assign this to be somewhere here with this arrow bar here. So now we see that these type of detectors here give you very good angular resolution, because now you see that these arrow in the angular part, the perpendicular one to the line, are very narrow, and I can make them even narrower if I add detectors. But I'm still sacrificing the position resolution. So I don't know very well where it's happening on the radial side, but it's very easy to fix that as well. All I need to do is to also increase the number of detectors along the radius. So how would I do that? Well, I start making many detectors, as small as possible, all around the source. There we go. So this is where the source would be, at the center. And you can see that if I do that, each of my interaction, let's make, for example, one interaction here, would give me a angular resolution that is proportional to, or inversely proportional to, the number of detectors that I put around the source, and also inversely proportional to the number of detectors that I put radially out from the source. So this type of detectors here, we can think that right now is it really maintains all the capabilities of the large detector fully encompassing, plus also maintains the capabilities of reconstructing the position of the interactions, both in terms of just XYZ as well as the angular distribution of the particles. Okay, so I'm going to stop for a minute, and let's try to see if there are any questions in chat about what we discussed so far. And you know, please write anything that wasn't clear, and I can go back to that slide. And or, you know, if there is it can be also unrelated to what I just talked about. Maybe there is a detector that you saw, and you know, it was you would like to learn more about, or something that I said that you would like to learn more about. All right, let's do another 30 seconds, just in case anybody is typing up. Otherwise, okay, good question. So this is this is exactly the kind of questions that I like to answer. So how do you determine the position resolution if two particles hit the point at once? Yeah, so like this is really the properties of a detector to determine whether two particles are the same particle or two different particles. Now, you will not be able to these two topics, the position resolution and the pileup. This is what you're describing here is the pileup event in which the particle is followed by another particle, and you cannot tell them apart. You would not be able to tell the two particles apart. So not only would you not know where the interactions, in this case, the two interactions are taking place, but you would also you would also just assign the single interaction. You would think that there's only one interaction, and you would just think that it's at the center of the detector, unless you have the equipment that can tell you. But in this idealized version, it would just be somewhere at the center of the detector. So yeah, now how can you help the pileup? How can you reduce the amount of pileup, or how these type of events, these events that are detrimental to your experiment? Well, you can make the detector smaller. The bigger the detector, the higher the chance there is that you're gonna get more events in a single detector. If you make the detector very, very small, there's going to be some situations in which the particles are emitted in the same direction, but there is a different situation that's like some exotic physics that one would have to create some certain effects and maybe deviate from the particle. If there is only one detector which is placed some distance away from the source, then there is a possibility the particle might get absorbed. So why do you place detectors? So that it might interact with the best possibility. Oh, I see. So how do you place the detectors? Yeah, so you're asking like the particle might get absorbed in somewhere between your the point source and where the particle is actually like where the detector is. That's a good question. So in this case here, like the particle would travel in a straight line and would not get absorbed if there was nothing in here. If there was just vacuum here, it's fine. So that's the particle is just going to go through in a straight line. There is no chance of it getting absorbed. However, of course, we cannot just have vacuum over large distances, or we cannot even have perfect vacuum even in small distances. So how do we deal with that? Well, depending on what particle you're looking for. For example, for neutrons or for gamma rays, well, the air in the room would not represent a huge amount of possibility for interacting. Although, if you build something that's a kilometer away, then maybe the neutron has starts really to be able to get absorbed. Interactions with oxygen, interactions with the water in the air. But if you really wanted to reduce this effect as much as possible, you want to reduce as much as you can the amount of material that is interposing between you and your source, like your detector and your source. So in this case, some situation you do build some vacuum that is gonna, like this whole detector system will be in a vacuum, and so the particles that are traveling in a certain direction can travel as far as they want without possibility of getting scattered or absorbed. That there's still going to be some possibility, because even in a vacuum there's going to be some leftover material, but you can really reduce it to the point where it's basically it's a good approximation. So that's actually what they use a lot for charged particles. And in charged particles detectors, you will see that everything is evacuated of air, and because a charged particle will interact very strongly even with the normal air. Like a standard pressure particle is just going to lose a lot of its energy even through traveling through air. So yeah, in that situation you would want to try to get rid of everything that stands in the way between you between the detector and the source. All right, I think that's all the questions that okay. Does the energy of Newton impact? Yes, of course. Yeah. So if I guess what I what I said about neutrons don't really, they can pass through more material. Well, in general, neutrons can pass through more material than charged particles. However, if we get a very slow neutron, the slow neutron, they tend to get absorbed very easily. Fast neutrons, even just a few tens of keVs or hundreds of keVs, they really can go. They have a much longer path, like the much longer mean free path in air. So yeah, the highest the neutron, we call that, like the higher the energy of a particle, the harder the radiation, and that means that it goes to materials more easily. And yeah, so the energy of the neutrons would make it easier to pass through any materials. The energy of the gammas would also make it. So regardless of the particle, the higher the energy of the particles, neutral particles, charged particles also to some extent, but for a neutral particle, the higher the energy, the more it's just gonna pass through the material unaffected. And material in this case, I mean air, even like just any material. All right. let's move on to the time and energy resolution, which is the second half of the presentation. And please, if you still have questions about that, first of all, keep keep putting them in the chat. I'll get them after at the end of this, and also at the end we'll also just have another Q&A, and you can ask about anything that we covered so far. Okay, let's talk now about two more properties of detector that are affecting the how they measure some properties of the particle internally. These are going to be some properties that are kind of dependent on the geometry, but are very much dependent also on the internal structure of the material that you create the detector out of. So let's see here what the time resolution is. The time resolution is the capability of a detector of determining the time at which an interaction took place. So if I have a particle that, if I have a particle that starts from somewhere and simply arrives at my detector at, let's say at noon, what time is it now? 1:38 p.m. Like basically the time resolution of a detector would be how many significant figures can I get on the time that the particle actually took place. So how many zeros would I be able to put, or how many significant digits would I put in there? Now, this is very rarely the case where we express an absolute time of when a particle took place. Much more common is to express things in relative times. So not like at what time of the day did a particle take place, but at what time difference with respect to another signal the particle is does the particle arrive at the does the particle interact? So for example, this could be a T interaction minus a T trigger. So this would be maybe the difference between two detectors. And in this case, it's very interesting to also look at how the two resolutions give the same, like one combined resolution, one combined time resolution. Now, as I say here, the time resolution depends on many effects. Some of them are kind of geometric in property. So, for example, for some scintillator, it's going to affect. Like I'm sure that you've seen some lectures on scintillation. Some of those properties of the scintillation process are going to depend on where the particle is taking place, and the closer, the smaller the cell of the volume of the cell is, the more the time the time to create a signal is going to be uniform, and therefore the time resolution is going to be improved. Other properties, of course, are, for example, how fast the signal is created and what are the exact mechanisms that created that signal. If just as a general rule, like if the information carrier, if what actually is creating your signal moves slowly, then you're going to get a worse time resolution. If what you are creating is is moving fast, then you're going to have a better time resolution. So to give an example of that, we can think, for example, what is the information carrier in something like an ionization chamber, something where you have heavy ions like nuclei or protons carrying the information. Well, these particles, given the same energy, they move slowly compared to light charged particles. So in that case, you would have kind of a slower time response. A detector where instead of information carrier, so what actually creates your signal is electrons moving, then would have a much faster, a much better time resolution. And lastly, what is the thing that moves the fastest of all? It's light. The speed of light is an unbeatable speed. So whenever you use light to transmit information, whenever light is the one that builds up your signal, then you're going to have a very, very good time resolution. And this is also the reason why in some applications you want to use detectors that are scintillator detectors, but that's not always the case. But scintillation detectors, which is a lot things that we study a lot here in Michigan, are actually the detectors that give you some of the best time resolutions. Now, the best way to measure the time resolution is to measure the spread in something that is known to be always the same. And we're going to see this pattern actually to exist throughout many different types of resolution and measurements. So the best way to measure the time resolution is to know that two interactions take place at the same time. Well, this is not always something that we can know for sure, but we can approximate it. There are some particles, there are some reactions that create particles always at the same time. So for example, sodium-22 creates a positron, the positron decay or beta plus decay, that then decays into two gamma rays, and those two gamma rays are going to be created like at exactly the same time, back to back. So that if I want to measure the time resolution of these two detectors, all I need to do is, knowing that the two gamma rays are going to interact with my detectors at the same time, I want to see what my measurement tells us. Now, in the real world, in an ideal world, the measurement of the delta T between T1 and T0 would be a straight line at 0. The two particles, whenever I measure particle 1, I should have also measured at the same time particle 0. Now there are some effects that go on top of that. Well, first of all, the particle doesn't have to interact at the face of the detector. So maybe the first particle here interacted at the face and the second one interacted over here. Well, already, you can see that there can be some spread just coming from the geometry. That's why I said, even though these are more internal properties of the detectors, there are still going to be some geometric properties of the detector. And small detectors, always a good way to go. So you can imagine that this effect here is going to create some spread in the distribution. Sometimes T0, like the particle going to the left, is going to interact earlier, and the particle on the right is going to interact later in real life. And it's going to create a small spread. But that's not the whole story at all. The real situation is that the signal themselves, there is going to contain some uncertainty. And that's what we call the time resolution. The time resolution, a lot of that is going to come simply from the fact that the signal is going to have noise in it. It's going to have some uncertainty about when it actually happened. And the spread of the signal is going to look like that. Very, well, not very wide, but it's going to be a wide end. It's not going to be a peak, like a single line. It's going to be wide. And the better the time resolution of your system, the more these lines, this curve is going to come down. And, I have this plot here showing basically the same thing. That shows that if I know the two interactions take place at the same time, for example, here the T1 and T minus T0 on average should be 0. There is still going to be some spread due to noise, due to time resolution, and we can quantify the time resolution by taking this spread. So we say that, for example, this spread here is of the order of, it looks like about 2 nanoseconds. Maybe a better detector would be 1 nanosecond, or 0.1 nanoseconds. You can make it. For certain detectors, you can get very, very good time resolutions. For some detector, you get very, very bad time resolution. Just a note here, if we were performing this measurement here, we have to go back to what I said in the earlier slide, where we haven't measured the absolute time that a single detector is taking place. We're measuring the time difference between two things. And when you measure the difference between two things, just from your introductory error analysis, you know that the errors are going to add. So the uncertainty of the two quantities after you subtract them are actually going to add to one another. So that this quantity here is actually larger than the time resolution of any single detector. Now, if the two detectors are identical, you simply divide this spread here by the square root of 2. So you would divide by 2 if the two errors were the same, but because the two errors are independent, they're not always going in the same direction, you divide by the square root of 2. This is something that results from this summing quadrature, which is outside of the scope of today, but just something that I wanted to mention. And going to the perfect detector for the time resolution. So what is something that is perfect for time resolution? Well, no, this should say time. Sorry about that. Well, if I want to measure something as perfect time resolution, we can go back to this plot here, or this figure here, and we try to do something that with, taking that example and making it as good as possible. Now, the distance to the detector doesn't really matter anymore. You can have a detector that is right next to the source. You can have a detector that's very far away. Of course, your efficiency is going to go down. Your angle, the position resolution is going to go down. But in reality, the the source, the detector where it's going to happen, it's not too important. There's going to be some angular effects if you get too close to the detector, such that there's going to be a bigger spread in where the interaction is taking place. But if you're far enough that the particles basically are straight lines coming in, then you can this time resolution is going to be not super dependent on the distance. It will depend, however, on the size of the detector, more importantly, on the thickness of the detector. So how many different places can the particle take place? Now, these different places can tell us, they would have different different ways of transmitting a signal to the detector, to however we're going to get the detector from to our system, to our computers or whatever. So depending on where it hits, it could have different interactions that have different times to create the signal. But the most important effect is, what do the pulses look like? So in any detector, there's going to be some kind of charge creation, some kind of charge creation that is going to lead to the creation of a pulse. Now, the faster the pulse is, so the faster we can build up the signal, the better the time resolution is going to be. So if I were to design a perfect time resolution detector, for example, I would use something that is created instantly and is perfectly, very quickly propagated to my system. And this can be done, as I mentioned at the beginning, using scintillation detector. If I wanted to design something that's maybe a bit worse, I could use something that is a light charged particle. So things that still move, maybe relativistically and at very fast speeds, but not as at the speed of light. In this case, I can make something that is, for example, electrons and holes. I don't like, this might be something a bit too advanced for now, but electrons and the absence of an electron travel pretty fast in certain materials. And then I can make something much slower, for example, by measuring the ions. So like the worst detector would be something that's, well, not the worst, but the worst common detector would be something that uses ions, heavy ions, to transmit the signal, because you would need a very long time to build up the same signal. Okay, so let's see, there appears to be a question in there that I'm going to try to take now. Is it counts versus time difference chart? What is y-axis? Yes. That's a histogram, exactly. Yeah, counts versus time difference. So every time there is you have two interactions in the two detectors. That's how I build up this graph and this is not real data, of course. This is just an example. But yeah, it would be every time you have two interactions and two detectors, you histogram that time difference. And in this case, it looks like this plot is actually normalized to try to give some kind of probability distribution, but it doesn't matter because all we're interested in is the width. So it's just about how wide it is, the histogram of the time difference between the two. Of course, you need the two, both interactions to take place. In certain situations, you might just get one particle interacting, the other particle just goes through. That particle would not be anywhere on this plot here. Okay, so let's go to now the energy resolution. Okay, there we go. So let's see, 150. Okay. The energy resolution should make, like, if the time resolution made sense, the property of a part of the detector to identify and to correctly report to us, the people who are making experiments, the timing of a particle, energy resolution is basically the same thing. It's going to be the capability of a detector to properly assign the energy deposited in them. Now, there is going to be some other ways that energy resolution can be used, and this can be like derived ways. So I wanted to just mention, in this case here, I say energy resolution based on the energy that is deposited in a detector. It's not always the case. In some situation, you can find, for example, a time of flight spectrometer, something that uses the timing of the particles to assign an energy. In that case there, I usually just think about that as being a time resolution with some adjusting factors. The energy resolution, as we're going to interpret it now, is going to be only based on the capability of the detector to determine the energy deposited in them. Now, the example that I show here is something that is based on the previous example there, where we have, instead of having something that we know is always happening at the same time, two interactions that always happen at the same time, we might have two interactions that, or like an interaction that always deposits the same energy, such that the spectrum looks like a straight line at some point, always the same every time, so counts on this axis here, and a certain energy every time. Now, if I want to know what the energy resolution is, I let the particles interact with my detectors, and I see what the measurement of these energies are. Now, I have to assume that these particles are depositing all their energies in a detector. As I say here, let's assume that for now they deposit all of the energies, such that if this detector was perfect, it would be a perfect peak again. However, there's going to be noise. So sometimes, the signal that is created by the particle is going to mix in with some intrinsic noise of the detector, and it's going to start creating, for example, a small shape like that. Other times you can have differences in how the detector responds at different positions. Again, the smaller the detector is, the more uniform it usually is, but in general, like you can have different non-uniformity, you can have non-uniformity in the detector. It can even extend this resolution even larger than that, such that even though the truth is a single line at zero, when you measure it, it's going to have a spread to it. Now, basically said in the same way way that the time resolution was expressed, we can also express the energy resolution as a spread of a Gaussian. So it's in the spread of the data when the data is the same every time. One way to do that is to determine, for example, if I have a cesium-137 source or some kind of gamma ray source or any kind of source, and I know that all the particles are depositing all their energy in it, I can histogram the signal that comes out of my detector, and I can characterize my energy resolution simply by looking at the width of that. Now, ignore this arrow here, or for what I just said, ignore this arrow here. But in certain situations, the particle does not deposit all its energy in a detector. In some situation, if I have, for example, on a scintillator, you would not have something that looks like that for a monoenergetic source. You would have something that looks like a Compton edge. What is the spread of this Compton edge, and how is that what we should call then the energy resolution? No. So in that situation there, the main assumption that we made at the beginning, that the particle always deposits all of its energy, is broken. So that's not a measurement of the resolution. However, we still can restrict certain interactions in which not all the energy is deposited, simply by measuring the amount of energy left over in the particle. So for example, this cesium-137 source might start off with 0.662 MeV and leave with like 0.2 MeV. If we measure this particle here, or can somehow determine it simply by, for example, finding the angle between the two interactions, we would know exactly how much energy is deposited. So in order to find the resolution, one has to know exactly how much energy is deposited in the detector, and then see how much the detector is reporting back to us. A very common way of reporting the energy resolution is not simply by saying how wide this is in some kind of MEV or KV scale, but it's usually as a percentage. One way to express it is by using the sigma, so just by looking at the standard deviation of what the spread of the distribution is. Probably a more popular one is by looking at the full width of half max. So this is something that it defines how wide my distribution is when it's at half of the maximum of the curve. And just for a lot of curves that look like Gaussian, it's about 2.35 times larger than the sigma. So that's the standard deviation. So how would you design a detector that maximizes energy resolution? Well, first of all, you would want to reduce noise as much as possible. We said that the main source, from our diagram here, we said that the main source of energy resolution or energy spread in this case was the noise in the detector. Things that once you have the interaction taking place, it's going to add up to some background noise. That's not the only way that it can be done, but let's look at that, for example. Let's start with that. So reducing noise. Reducing noise means that I want a detector that when nothing is happening is reporting nothing back to me. So that when no interactions are taking place in the detector, no energy is being measured by our system. So if I look, for example, at the signal as a function of time, a bad detector is going to have a signal that looks like this. And a good detector is going to have a signal that looks like this. It's going to be very hard to minimize the noise in a detector, like to zero, and but it's possible to reduce it by a lot. Now, this, of course, this is ideal, but how do we actually reduce noise in a detector? Well, we first have to understand what is noise coming from. Noise is basically random interactions or random things that can happen maybe like down the line in your detector system, like in your readout, or it can happen at the detector itself, where simply randomly certain interactions are going to create a small signal. And all these interactions, over time, they build up to a certain background pattern. And this is usually created by some real events, some physical events. And most of the time, this is thermal, like a thermal type of noise. So if I want to minimize the noise as much as possible, I want to minimize the amount of things that happen as much as possible. And that's done by reducing the temperature of the detector as much as I can. And that's why in certain situations, if you look at certain like expensive detectors, calorimeters, for example, you see that they are kept at extremely low temperature. What that does, it means that the random things that can happen inside the detector, all the particles of the detectors, all the atoms of detectors are sitting there motionless because there are such low energies, such that there is not really a lot of noise going on throughout. There might be other types of noise, but that type of thermal noise that you have inside the detector is really minimized by reducing the noise, by reducing the temperature as much as possible. Now, another important way that you can reduce noise is what we're going to talk about: maximizing information carriers. Okay, this is going to be something that maybe later on is going to be explored a bit more, but it's also something that I wanted to discuss because it can create some intuition as to what detectors are good for what. And also, if you want to judge or compare two detectors and one has a certain property and the other has a certain property, you want to know how that is going to affect your energy resolution. Now, the information carrier is basically something that goes from where the particle is interacting to you, the experimenter. So in a scintillation detector, the information carrier would be the photons created during the scintillation process. So the particle comes in, it creates photons. Some of those photons are going to be able to get to the PMT. Some of those, and transmitted and all the way to your detector. So if I have a certain amount of photons, if I have a low amount of photons, then a low amount of photons are going to make it down into the PMT and all the way to my system. If I have a large amount of photons, the same thing, there's going to be more of them. Another example, just to give you some intuition, would be something like a solid state detector, where in that case, the information carrier is the number of electron hole pairs created along the track. Now, why is it important to maximize the number of these information carriers? Because in a lot of applications, in a lot of the detectors, there is going to be an uncertainty on the number of particles created. It's going to be proportional to the square root of n. This is the famous counting statistics uncertainty, such that if I want to minimize the relative error of the relative error with respect to how many information carriers there are. So let's say that there are 100 photons created per nuclear interactions, then I would have plus or minus 10 photons, such that this error will be about 10%. Just because there can be more or less photons created within a single thing due to some counting statistics. It wouldn't be exactly 10%, like it wouldn't be exactly just as proof, and it's proportional to it, but all the same things apply. If I had, instead of 100 particles emit 100 scintillation photons emit per reaction, if I had, for example, 1 million particles, now my my counting statistics would only add 1,000 of them. That's the square root of the number, such that my energy resolution is now 0.1%. So we can see that by improving, like by increasing the number of information carriers, I can improve my energy resolution. And that's why in a lot of situations, you want to try to get as many information carriers as possible. When you buy a scintillator, you can see how many photons are created. They report how many photons are created at a certain energy. And good detectors would have a large number of photons, and scintillation photons, and bad detectors have a few of them. So combining these two things together, we can see that we can really get a good value for the energy resolution. Okay, let's see other resolutions. After this, I'm gonna take maybe again a minute or so to see if there are any questions. What are the other things that one can measure? In this case here, as I shown at the very beginning, we talked about how to measure the location, the space, and the time of the particles, the momentum, the energy, and the direction, again, just the angular component. And we can see that this kind of covers what I talked about at the beginning, but there is still the thing about identifying which type of particle it is. So we said that those properties apply to each particle individually, but there are still some things that some internal properties of the particle that can be measured. I didn't cover those because this is for more advanced detectors, and this could be, for example, the charges of the particle, the masses of the particle, and the spin of the particles. These are all internal properties of the particles that with good detectors, with advanced specialized detectors, one can investigate. There would be, for all of those, it would be like a charge resolution, a mass resolution, a spin resolution. What is interesting about this is that most of these properties here can also be inferred from the other resolutions there. So for example, the masses of the particle and charges of the particle would also be inferred from a position resolution or time resolution. So a lot of the times these properties of particles here are determined from the resolution, the kinematic resolutions that we discussed there. It is very hard to measure the internal properties of the particle directly, but it's very easy to determine, well, not very easy, but it's easier to determine how the particle moves in space, and therefore use the properties that we discussed today. Okay, so we have 2 more slides to go, but I'll take now any questions, because this is kind of a change of pace on like how do we interpret the signal of a detector. So let's see if there are any questions. How can particles measure with spin? How can, yeah, so I don't know if that, maybe that's a typo, like, I don't know if that was meant to be, how can beta particles measure with spin, or just how can particles measure with spin? So what I meant, actually, okay, maybe I see the confusion. Like what I meant is not that the particle is measured using spin, but we can use detector. Yes, we can use detectors to measure the spin of a particle. Not that we're not exploiting spin to measure the particle, but we're exploiting the detectors to measure the spin. And that's something, you know, like the most famous is probably the Stern-Garlock experiment. And what you're measuring there is the deviation of a bundle of particles based on the on a non-uniform magnetic field that you can apply, and you're going to see that the particles split into 2. And the stronger the magnetic field, the more the separation between spin up and spin down particle is going to be, and you're going to be able to measure. You're going to be able to distinguish whether the particle had a spin up state or spin down state, or if it collapsed into a spin up or spin down state. In certain other other characteristics, you can measure, for example, the polarization of a photon. That's similar to what the spin is for a particle. It's the polarization states of a photon is also based on the spin of the photon, and in the case is because the spin of the photon determines also the direction of the electric field, and or it's related to the direction of the electric field. So you know that if the particles created by the photon are going to move more in one direction rather than another, you can figure out whether the polarization was in one direction or another. This is all very similar to low energy physics. In low energy physics, these things are measured all the time. Quantum computers are basically just machines that measure spin. And the one other way that, for example, one can measure the charge of a particle, not the spin, but like the charge, would be as what I show here on this slide, where you can make strong magnetic field and see how the particle is affected by the magnetic field, how it starts rotating around the magnetic field. So yeah, the spin resolution would be something that is probably either something to do with the interactions of the spin with the magnetic field. So it would be some kind of energy resolution or the signal distortion. Or it could be something that is determined from position resolution. So in the Stern-Garlock experiment here, you have a very good measurement when the two things are separated very well, and they're separated very well when you have a good position distribution. Polarization is important for the measurement. No, most of the times things, like, it depends what you mean by important. Does it affect like a measurement that doesn't care about polarization? No, like in most of the times polarization is created uniformly. The number of particles created in a certain polarization and the other is just uniformly created and uniformly produced. However, in certain situation, you want to know that. You want to know what the polarization states of the radiation is. And in that situation, of course, it's important by definition. There are maybe some groups out there that are like trying to measure the polarization of a certain reaction. And in that situations, yeah, it becomes important. For normal experiments, it can have maybe like can introduce some errors if you just sum over all the polarizations, but it's probably smaller than anything else in here. Like probably just the thermal, the temperature in the room is probably a bigger effect than the polarization states, especially if you have decently sized detector. Yeah. All right. So I'm gonna try to go through these slides pretty quickly, but of course I probably have my email somewhere here. No, okay, I'll put my emails in the chat if anybody wants to continue the discussion or if there are any questions. But I'll just mention here what are the properties of the detector that makes it desirable, kind of from taking a step back. Throughout the presentation, I said, we measure the time resolution many times and we histogram the signal. So we histogram the signal coming out of the detector. So I often talked about what is the signal coming out of the detector. Well, in certain situation, we actually still don't know what the relationship is between the signal and the property. So for example, let's say that the property of a detector, and in this case, it's a very, very idealized property of the detector. It doesn't matter what it is. Like in certain situation, let's say that the property of a particle could be the energy, it could be the timing, it could be anything else, is fixed at this point here. The signal that is created, what we discussed so far is how wide it is with respect to how it should be. So we know that if it was a perfect detector, the width of this line should be exactly unit. It should be like a widthless line. So that would mean a perfectly like a perfect resolution detector. And we can see that this is one effect. So these three lines here can have all the same width at that point there. And so based on the discussion before, we would say that those three detectors have the same resolution with respect to that property that we just discussed. However, there is another thing, which is the linearity of the system. So we can tell these three systems apart. We can tell that the black line, the red line, and the blue line are different from one another, even though the width or the resolution of the detector at that property, at that when that property is one, is the same for all three of them. But we can still tell that the three lines apart. Why is that the case? Well, because we can see that one detector is linear, like the red line there is a detector that when your property is one, your signal is going to be some x, and when your measure property is 2, your signal is going to be 2x. That's something that we call a linear detector. This is the most desirable of all the detectors, because then you can simply take that you can simply take what you get out of the signal, multiply by some constant, and get out what the measured property actually was. Simply relabeling these axes here. Now, there is a second type of detector which is still usable. In that case, it's a detector where it would be the black line here. The black line here, you see that it's not linear anymore. You know, as you increase the measured property, let's say the energy, you get more and more and more out of it that in a non-linear way, such that when the energy is doubled, for example, you don't get twice the signal, but you get maybe 4 times the signal or something like that. And when this is the case, this detector here is said to be non-linear, but it's not a detector that we have to throw away immediately. It's not something bad, because it is still possible to take this detector and simply find a non-linear rescaling of that axis. We can still assign a value to each of those points there and reconstruct from the measure property from the signal the measure property. The detector that we should be very wary of, however, is the blue one. The blue one is a detector that we say it's not one-to-one. In this situation, we can see immediately, just by thinking about a situation where we could be measuring something with the blue line, that we might get, for example, out of the detector 2, 3, let's say, right there. And when we get 3 volts out of the detector, and then we ask ourselves, okay, what was the measured property? What was the value of the measured property? Well, one would just take a line throughout and say, well, my measured property was, and then you say, oh, wow, it could have been either here or there. So this detector here is something that would not tell us what the measured property is given the signal. In certain situations, one can make approximations and say, well, that's almost impossible, based on some physical theorem or something. And you just say, well, let's restrict our range to this. But these type of detectors are very, very bad because they're not one-to-one. And yeah, so how do we create these lines here? This is basically the last point of the presentation. The last one was basically repeating what I said there. What we can do, we can see that this line here with the bands around it basically completely determine the detector, the performance of the detector. So the average, like the shape of the line, will determine what the calibration of the linearity of the detector is, and the width of the line will determine its resolution, all with respect to some measured property. This measured property, as we said, could be energy, could be time, could be position, could be multiplicity even. And yeah, so making this type of plots here is very important when you try to characterize any type of detector. And yes, with this, I'll open up the questions if there are any. I know this was only 2 slides, but I wanted to kind of make some time for the questions regarding the first half of the presentation. So if there are any questions now, I'll probably be here for another 5 minutes. I do have something that I have to attend at 2:30. So, and I'm sorry I went a bit over time, but let me know if there are any questions now, and we can discuss them for a while. Thank you. Abbas, you can stop the recording now. I put my email there on the chat.